So when you build an electronic product and want to put it into manufacturing, you actually need to build two products, the one you're going to manufacture and sell, and the factory test system for it. This trips a lot of people up because they think they've finished their development. They're not even halfway there. And part of that is that nobody really talks about the factory test side of things. For most commercial projects, it's a very closely guarded secret. It's basically always put together in a hurry, so people are embarrassed about it and it's messy. It's fairly rarely open sourced, even for products that are otherwise open source hardware. And that makes it quite hard to find good information on best practice, and especially good low-cost practices suitable for small volume manufacturing, which makes this a really common trap for newcomers to manufacturing. I've been running into this for 10 years or so. I've built a few factory test systems, and I'm going to try and use that experience to give you some ideas of how to approach this and how not to mess it up. So first, I want to explain, what is a factory test for? What's the situation where you need it? Well, it's this. Your PCBs are flying off the assembly line and happening quite quickly. And the folks running the assembly line want to know, are these boards okay? Can we keep running the line, or do we need to stop it? It's probably not your production line, it's a contract manufacturer's, so they've got other customers waiting to use it, and this is a really big decision. Can you keep running? So you need a test system that's fast and that's thorough, and both of those things means it needs to be automated. So the testing is integral to the production process. It's how you check that the process is producing the outputs you want. If you don't have testing, you can't close the loop on the manufacturing process. People say, well, do we really need one? Can't we just build everything and test it later? Well, you might be able to, but if it turns out something was wrong, it's wrong on all of your boards. And now you can't afford to rework them because the cost of that will sink the whole production. Can we just do all the testing manually? Again, maybe, but as the product gets more complex, you can't do it fast enough, thoroughly enough, or consistently enough. What should a factory test be testing for? This is another thing that people get wrong a lot, is it's a very different kind of testing to a lot of the other testing that you're doing in development or while going through regulatory testing or so on. You have, to borrow a term from security, a quite specific threat model. And that threat model is assembly errors, right? It's the processes that go on the SMT line are placement and soldering. And if the placement's wrong, you can have a missing part, a wrong part, or a part that's in the wrong orientation. If the soldering's gone wrong, you can end up with a short circuit or an open circuit because there's a blob of solder across two pins, or there's a pin that didn't take. What's the output of a factory test? Another common mistake here is it's not just pass or fail. Pass is a great result. We like pass. Fail is an absolutely useless result from a factory test because it does not tell you what is wrong. And you don't want to know just what is wrong, but what are the possible causes of that? And hence, which components on the board need to be suspected, and what should the factory do about it? That's actually what the output of the factory test is what should the factory do about it? How fast does it need to be? Well, my rule of thumb at this point is to aim for about a minute or less. You're probably not going to test every board as it comes off the line. The typical scenario is when they start up the production on the line, they're going to test every board out of the first few panels, and if everything looks okay, they're going to keep that line running, and they'll test a few percent randomly selected out of the boards coming through. The rest are going to be tested later. That testing later takes up a significant amount of time. If you're building 2,000 boards and you have a 1-minute test, that's a 35-hour week just of running the test, right? In practice, longer. Right? And every second you add or take off the test time is another half an hour added or subtracted from that week of testing for 2,000 boards. What does a factory test consist of? Well, it looks something like this typically. You've got your device under test, that's your hardware. It's got various components in it, and you've got to put a bunch of stuff around it to enable you to test it. So you've got to be able to put power into it. That power supply generally has to be programmable with current limits and measurement and so on. You're usually going to have to blow in some firmware or gateware, so you've got programming tools there. Your hardware's got various interfaces on it. You need to be able to put signals into those, so you've got some sort of stimulus, and then you're measuring various things coming out both of those external interfaces and from test points which are giving you insight into internal parts of the board. Very, very few products you can test effectively just from their external interfaces. You have to have test points, which means you have to design your product to be testable. I'm going to talk you through the test that we did for Cynthion. Cynthion is the latest product from Great Scott Gadgets, who you may know from other open source hardware like HackRF. It's a USB multi-tool. that you can use for packet sniffing. You can emulate USB devices with it. You can mess with USB traffic in transit. You can use it as a development platform for USB and USB devices. On this board, we've got a lot of stuff. We've got a microcontroller, an FPGA, we've got some fancy RAM, we've got 3 USB PHYs connected to 4 physical ports, we've got power switching so that we can route up to 20 volts and 3 amps through it, voltage and current measurements for all those ports, and there's LEDs, buttons, there's the PMOD expansion ports. So there's quite a lot of hardware on there to test. When you're looking at how are we going to test a given device, I like to do a table like this, where we plot out what are all the key components in this system, how are we going to test those? So what behavior are we going to look for that tells us if they're working? And then what does that mean in terms of what equipment we need in the test system to be able to do that? And remember, you're looking to catch faults here, so you're not trying to test every possible behavior of the system, but you're trying to think about what behaviors can I look for that if all those behaviors are okay, that covers all of the possible faults. So they give you an idea of the sort of set of test equipment needed. When we did this exercise for Cynthion, that table had 53 items in it, different behaviors to test. Many of those in turn had to be duplicated for each port on the board or different test conditions. And that gave us this set of test equipment requirements. We needed a programmable power supply. We had 44 test points we needed to measure on the board. We had to make sure those test points were present in the design. We needed SWD programming for firmware. We needed USB high-speed host and device that could communicate through the device under test. And we needed loads that we could put in so that when we put current through the device, we had somewhere for it to go. Right? Now, you have probably have a lot of equipment already on your lab bench that can be used as part of a factory test. So traditional stuff you find on the bench like power supplies, multimeters, oscilloscopes. Many of these things have some control interface on it, which you can use to remotely control the hardware and read measurements out of it. And in fact, everything on this slide is a piece of hardware that I have used in factory test systems through open source software, in particular the SIGWOC library. There's some downsides to this, though, which is this stuff can be expensive, especially when you buy it new. And even though you might get a good deal on eBay on one of these things, you very often find yourself needing more than one test station. And then suddenly you need 3 more, and it's looking like a very expensive set of stuff. It can also be quite bulky, in particular some of the big old school power supplies, which are lovely to work with, but not fun to carry on a plane. We made some decisions whilst planning this test. We decided we were going to design custom hardware for the test. There are approaches you can use to try and avoid that, but they tend to lock you into proprietary hardware and software. We decided to try and avoid off-the-shelf test equipment as much as possible and build things into the test system, which really simplifies the problem of building and shipping multiple test stations. But that meant that we were going to need a 20-volt, 3-amp programmable power supply built into the system. We decided to use GreatFET as the control platform. I'll say a bit more about that in a moment. And we decided we're going to open source every part of this test. This is all developed in the open. All the hardware and the software that I'm going to show you here is there for you to look at and to reuse bits of in your own projects if you want to. GreatFET is another Great Scott Gadgets product. It's a USB-controlled I/O board based on a LPC microcontroller. It's got all of the usual peripherals you'd expect out of any microcontroller in that class. The key thing that made it really good for this project is that it's all set up to work through a Python API from the host. So we didn't have to write any custom firmware for this board to use it in the test system. We didn't have to define a protocol between the host and the I/O board. We could just sit there and start writing Python. The overall sort of concept we came together here was that we have the device under test, sitting on some test pins that contact all the test points, in a board that supports it, the pins. We have some USB cables that go to the ports. Those actually had to be custom items because USB-C is a bit weird. There is not a pin on one end of the cable for every pin on the other end of the cable. We've got the GreatFET acting as a sort of test controller attached to another board that we call Tyco, which has got all the custom hardware that we need to implement the test. So look at that as a block diagram. You've got the device under the test at the top. Tyco mostly consists of switching and multiplexing to get all the different signals and power supplies and so on to where they go. And it's got the programmable power supply, a USB test device. We use the test PC as the USB test host. And then you've got the GreatFET, and we use a Blackmagic probe for the programming. These are the board designs. Thank Taylor Streetman for this, did most of the board design work. So Tyco, you can see things like the analog multiplexers at the top. There's USB signals routed around through different switches and so on. And the other boards, which we call Sassarides, is just test pin support, basically. One thing I really like about this is this little programmable PSU. It's a very compact little bit of circuitry. And the reason we could do this is basically because your USB power supply for your laptop these days is basically a programmable bench PSU. That capability is now built in, which means there is single chip solutions you can use that will give you a sort of 0 to 20 volt, 0 to 6 amp power supply that has current limits and can measure its own output, right? So it's not as good as a proper bench PSU, but it's good enough for our purposes. And this really simplifies the test system. So you can put all this together just on the bench in a cardboard box and screw a Cynthion board down to it to work on developing the test. But when it comes to using it in the factory, you need a test jig, like the one I've got on the table here, right? So what that adds on top of your cardboard box is a way to quickly open and close, to load and unload a board fast. It protects the test points so that they're not exposed when the board isn't in it. And it spreads the pressure of pushing that board down across it so that you're not bending the board and possibly breaking shoulder joints from the force of all the test pins on it. Oh. We good? Yeah. When I first built a factory test system, I built my own jig. I've talked to 3 people in this room who've also built their own jig. Don't build your own jig. You don't need to build your own jig. If you visit your contract manufacturer, they will have a room like this full of jigs. Look at them. They all look the same. This is a solved problem. You can get them off the shelf, or you can have them made to your requirements. It's fairly easy. It doesn't cost too much. You do not need to solve this problem yourself. What you do need to solve is your test software. And you should not underestimate this. It's actually quite hard. And the reason it is hard is that your normal firmware software only has to deal with one hardware configuration, the correct one. Your test software has to deal with every possible wrong hardware configuration without screwing up, without giving you the wrong answer, without damaging the already broken board under test, and giving you useful output. So this is something that's going to take you time. And you don't just have to write that software, you also need to document it, you need to provide training for it, and you need to provide support for it, because you are probably not going to be the person using it. It's the folks on the line at the factory who need to be able to use this. So they need to know how to set it up, run it, how to respond when it gives them a fault, and how to get support from you. And you need to think about how you're going to streamline that process. Something we've settled on is this system for failure codes, where we have some numbers that identify which step of the test failed, a 3-letter error code that says how it failed, and then that lets people easily share what the problem was, and group boards by which failures they've had, and things like that. So in the event of this case, we can tell them, okay, these are the components you need to check. The software for this test is written in Python. I actually started writing this before the test system hardware design even started, because I found it quite a useful way to plan out the test sequence and just write placeholder functions, fill them in later. So we could run through this. And in the process of writing it, sort of built out this framework that deals with the various display, logging, error handling, and so on, so that the actual test code is kind of as simple as possible and just gets the key features of the test. It's very important to get the right sequence of tests, to do things in the right order, right? It's very similar to manually bringing up a board that you've only just built and you don't know if it's any good at all. You need to check all the basics first. Is everything connected that should be? You know, is anything shorted? Okay, now maybe we apply some power and look very carefully before we do anything else. There's no point doing complicated tests when it turns out one of the power supplies isn't right or something like that. It's very easy to damage a board that is already faulty by applying power to it and there's a short or something that's wrong. So as much as possible, you want to be checking the system for shorts and things like that before applying power, looking for resistances, are they as expected? And when you do apply power, it needs to be limited. And as soon as anything looks wrong, you need to stop. One thing that can make factory tests an awful lot simpler is having self-test capability in the system, right? You've already got probably a microcontroller or an FPGA or something in the middle of the system that's connected to everything else. Great, that's now part of your test system. Use it to test the other stuff. And something you can do that really helps with that as well is the interfaces that you use to program that chip, you can often also use to interface with it and communicate with it so that you can communicate with your self-test program and coordinate with the external hardware. So some statistics on this test. Out of those 53 behaviors we wanted to test, it turned into 918 individual test steps, and it takes us about 58 seconds to run that test. We're doing 15 to 20 tests per second. We have put 5,000 boards through this test now. And because of how thorough and effective this test is, we have only had one board from a customer that was not performing in the field and that we've had to replace. And it was because of a behavior that we did not test for. So if you test things, you will get them right. If you don't test things, you're taking a gamble. I'm going to, in fact, I'm so confident of this test, I'm going to do a live demo of it. So take you through this. So you have your board. It goes in the test jig. It sits on some locator pins. You just go ahead and close that. You connect 3 USB cables to it. And then since you can't see my screen, we're going to run a video at exactly the same time of doing the same things. 3, 2, 1, go. So first thing, it tests the board for shorts. Then it applies power, slowly, gradually ramping up voltage and current. Now we're loading some firmware onto it. We're checking everything looks correct. We're loading self-test gateware. We're running the self-test. The FPGA is checking all the other hardware connected to it. Once it's done that, we've got confidence in the rest of the system. We can use that to test other features. Now we can test high-speed communications to each of the USB ports. We're loading the gateware into flash that it's going to ship with. Reload the self-test gateware. And now it's going to prompt me to attach another cable. Push a button. And now it's doing the high power, high current tests using that programmable power supply to put up to 20 volts and 3 amps through. We can do this now because we've got confidence of the basics. And that runs through all that, checks that all the internal resistances and everything are as expected. And then it's going to prompt me again to look at the LEDs and just visually check that those are all correct. There's a reference set on the test jig for me to compare them to. I pass that, and then it just wants me to check all the buttons by pressing them. And that's the test, 58 seconds. So if you want more info, on the Great Scott Gadget site, you can read more about Cynthion and GreatFet and HackerF and all the other products we've got there. All the hardware and software for this test is on our GitHub there. And if you'd like to contact me, that's some details. And if you've got a test system you'd like to build, I'd love to help you.